So the graph of the function f of x is shown at the right. Which of the following statements is false? X equals a is in the domain of f. Well, if I go to a, it's defined up here, so this guy is true. The limit as x approaches a of f of x exists. Well, again, here's a. If I come from the left and I come from the right, it's approaching this height, so yes, this does exist. The limit as x approaches a does not equal f of a. Well, that's true also. The limit is this height here. F of a is defined here, so this guy is true. Well, it must be this guy, but let's make sure. F of x is continuous at x equals a. Clearly this is not continuous. There's a hole. In fact, we would call that a removable discontinuity. So this is my guy that's false. So this is my answer for number 1. Number 2, we're looking for the limit of this rational function as x approaches 0. If x is approaching a constant, we first need to plug in or do something so that we can plug in. The only time we look at top heavy or bottom heavy is when x approaches infinity. But this is approaching 0, so let's factor this guy to see what we have. Because if I plug in 0 now, I'll get 0 over 0, which is indeterminate. So I need to do something more. So let's factor out, there's a GCF of 2x cubed, and I'm left with x to the third plus 3. And in the denominator, I can factor out an x cubed, and I'm left with 4x squared plus 3. Well, now I can plug 0 in. If I plug in, well, these guys cancel. So if I plug in 0 here, I get 0 plus 3 is 3. 2 times 3 is 6. In here, if I plug in 0, this is 0 plus 3, I get 3. And so 6 divided by 3 is 2. Oh, here is my limit as x approaches positive infinity. Now, since it's a rational function, I'm looking at top heavy or bottom heavy. So I'm going to circle the lead-in term in the numerator. That's x squared. The lead-in term in the denominator, that means I take the whole thing with the sign in front of it, is negative 4x squared. And this guy reduces to negative 1 over 4. Okay, number 4. If a does not equal 0, it can't equal 0. Well, because we can't have 0 in the denominator. They want to know the limit as x approaches negative a of this guy. Well, if I see this, I know if I plug in negative a, I'll get 0 over 0, so I need to do something. So when I look in my numerator, I see dots, and right away I'd like to do this, because I see that right away. And I have dots here again. So this is x squared minus a squared, x squared plus a squared, but oh, look at that. This is the same as this, right? Isn't this right up here? So this divides to 1. So I'm left with 1 over x squared plus a squared. And I'm looking for this limit as x approaches negative a. So I plug in 1 over negative a squared plus a squared. Well, this becomes positive a squared. So 1 over a squared plus a squared is 2a squared. And so that's my final answer. Number 5. So they give me this piecewise function, and they're telling me that f is continuous at x equals 0. If it is, then what's k? Well, if it's continuous, then these two pieces must be equal to each other when x is 0. So I'm going to plug in 0. Right? I'm going to plug in 0. So I get 0 squared minus 0 over 0 minus 1. And that must equal k if they're continuous at x equals 0. Well, that just gives me 0 over negative 1 equals k. 0 over negative 1 equals 0. So k must equal 0. Next, find all values, all x values, if any, at which f of x is not continuous. And then it says to describe each discontinuity. So we have to describe each. So in order for me to recognize the discontinuities, I should first factor and see exactly what we have here. So in my numerator, I have x plus 1 times x minus 1, that's dots. Here I have a GCF of x, and then I'm left with x plus 1. So remember, the factors that I can cancel, that's where my whole is. So x equals negative 1, that's where I have a whole. And if it's a whole, then I have a removable discontinuity at x equals negative 1. And then in my denominator I have x. Well, it's in my denominator, so x cannot equal 0. If it does, x equals 0 is my vertical asymptote, which means it is an infinite discontinuity. And so I've named all my discontinuities. Up here, that's just an x-intercept when I set my numerator equal to 0. Okay, so now evaluate each limit. So we need, when I see these guys, like 7 and 8, I have to remember that the limit as x approaches 0 of sine theta over theta equals 1. This is the fact that I need to use in order to solve these. And so we can let theta equal, in this case, 5 theta. So I can rewrite this as the limit as x approaches 0 of sine of, right, this is my 5 theta over 5 theta